it's always above the x-axis. So if f prime is positive, then what's that tell you? What's always increasing? F is increasing. So then when they want to find the max value of f, and f's always increasing, where's that going to be? At the right end, right at the right edge when it stops increasing. So at 6. So it's a fair bet that at 6 it's going to be the max. So what we're really trying to find here is what is f of 6 is what we're saying. Right? What is the function value at 6 is really what we're trying to figure out. Then the question is, how can we do that? Well, remember, we've done this before where we had an f prime graph, which this is, and then we wanted to think of the f graph, right? And that's kind of what this would be about. So if they tell you that f of 2 down here is 10, so if the f graph was up here at 2, it was at 10, then at 3, 4, 5, and 6, where is it? So you could do something like that. You could say, okay, what's happening? Let's start here. Let's just start here at 2. So what do I know about, what does f prime tell me right here? About 6. So, okay, you're looking at the y value here is about 16. So what's that tell me the f graph's doing? Slope is 16. So like over 1, up 16 kind of thing. Although, if I go over 1, up here at 3, the slope is what? It looks like it's about 26, 27, something like that. So maybe like an average might be something you could do here. So it's like 16 up to, say, 26, so that would average to be about, what, 21 or so? So I would say if we go over 1 on the f graph, we'd go up about 21, which would take me to where? 31. You see where I'm going with this? Because what I'm trying to do is see where the f graph would be at 6. So if I did it that way, that would tell me I'm at about 31. Now, if I go over 1 again, now I'm up here at about, I don't know, 32 or so. So if this is 26, that's more like 27 probably. But so between 27 and 32, that's an average of about 30 maybe, let's say, right? Would that be reasonable? So over 1, I'm going to go up 30. So now I'm up at what, 61? Make sense? And then if I go over another 1, I'm down here to 25. So between 32 and 25 is an average of about 28, 29, maybe. Let's say 29. So if I add on to that, that would take me to what, 90? And then between 5, so I'm at 25 here and down to 0. So that'd be an average of about 12, 13. If I add that onto there, that's about 103. Is that reasonable? So what are my choices? What was the answer? E, 110. I mean, I came up with that, kind of doing it roughly like that. I came up with 103, which would seem to be closer to that one than that one. Okay, and I might have been underestimating those a little bit. But now, like I said, when we get into areas, when we talk more about areas, that would be probably how you would do that one. We would essentially count squares, which might be a little more accurate, but it's not real accurate. But that's how we could do it now with the information we have now. And even later, once we learn about areas, you could still do it like what we just did there. Okay, seems kind of inexact, doesn't it? I mean, feels strange to be that's the best we can do, but sometimes that is the best we can do. I mean, approximations are a big part of calculus if you think about it. I mean, geez, the whole point of a derivative is better and better approximations, right? 2 points getting closer and closer and closer and closer, right? Limit, the idea of a limit comes in there. I mean, so it's not surprising that you get into some problems that are about approximations. Okay, anything else left over from sample 1? On the free response here. Okay, we can spend a little time talking about that. I have one other hint I'm going to give you on another free response that we'll get into talking about sample 2 here a little bit. Okay, so here they give you the function f, and of course x cannot equal -3 because that's going to be a problem. That would be 1 over 0. And of course, if you put in, and this is a no calculator, oh no, this is a calculator one, so you actually could graph it. But what does it mean? What would you expect when you do graph it? If you put a -3 in here, you 9 minus 8, you get 1 over 0. What would you expect in the graph if you got 1 over 0? Vertical asymptote, right? So there should be a vertical asymptote at -3. Then they tell you what f prime is. They just did a quotient rule, but they went ahead and did it for you because, quite honestly, they understand that some people have the CAS calculators like we do, where you can it'll just do the derivative for you, and some people don't. And so, to kind of make things fair, or whatever, and it's not a derivative question. They're not testing you in this question to see if you can do the derivative. They just give it to you, right? They just give it to you, so you can then use it. Kind of puts everybody on the same playing field in this problem. So anyway, sketch the graph of f. So all you have to do is type in your calculator, draw the graph. We know at -3 it's going to have this. Now what's it do? Is it go up like so here? Down? Like here? And then up here? That kind of thing? Is that what's going on with it? Okay. I don't really care. I mean, that's easy. You could draw that graph. But I'm guessing, Rachel, that wasn't your question probably on the graph. Find the range of f. Use f prime to justify your answer. So, when you do the range, now, I guess having the graph, let me see, you get your graph drawn. Okay. Having the graph wouldn't hurt here. And then, and then it's going to ask us about the range of f, okay? Okay, so we've got asymptote at -3. We've got this thing that's kind of coming up and then goes down like so, and then it kind of comes here. Does it come down below here a little bit? And then seems to kind of do this sort of thing, kind of. That's not really good. There actually should be a. This one kind of comes. There's actually a diagonal asymptote that goes right through like that. Okay. But anyway, so when they want the range of f, what are the key points that you would have to find here to do the range of f? Range, remember, is the possible y values. What are the key points on that graph you would need to know? The local min and the local max. You need to know those 2 points, right? And so, how do you find a local min, local max? Where the derivative is 0, right? So when they say use f prime to justify your answer, that's what they're talking about, right? Use f prime to justify your answer. They're saying we need to do the derivative. So what? So the derivative is a fraction. Well, where's a fraction ever 0? When the top is 0, so what do we have? X squared plus 6x plus 8 equals 0 is what we need. That's a calculator problem, so you could just solve it, but I think it's a pretty easy one. Isn't x plus 2, x plus 4 as far as factoring, right? But you could use your calculator, so it's -2, -4. So that makes sense. Kind of looks like here about -2. My picture's not real great. -2 and -4 is where those are happening. But what do we need? We need to know, because the range is going to be what? The range is going to be this y value up to infinity, and it's going to be this y value down to -infinity, right? So I need to know those y values. So where do I put them? Plug them back into the original, right? So I need to go to the original and plug those in. So -2 squared is 4. 4 minus 8 is -4 all over, what was it, -2 plus 3 is 1. So this one here is a y value of -4. That'd be right when I put in a -2. And then I put a -4 in, the square root of 16. 16 minus 8 is 8. And then -4 plus 3 is -1. So this would be a y value of -8 down here. Did I do that right? It wasn't the original function x squared minus 8 over x plus 3. Right? So I just need to know those y values. So my range is going to be negative. Usually you start from low down to little to big. So -infinity up to -8, including -8. And then from -4, including -4, up to infinity, and don't include infinity. So that would be a great way to write the range. Okay? So we need to understand domain and range. Domain is everything but -3. The range is the y value. So the you gotta understand what range is. Okay, then what about this? The limit of f prime as x goes to positive and negative infinity. Well, let's do that in red here. So that was x squared plus 6x plus 8 over x minus or plus 3 squared. That's f prime. And if I factored that out, it would be 6x squared plus 6x plus 9. So what happens to that as x gets really big? That should be easy. What is it? As x gets really big, high powers dominate. X squared over x squared, 1. Right? The coefficients of the largest terms. Remember all that stuff we did with that? What about negative infinity? Does it matter? It's going to be squared, so it's going to turn into, it's going to still be x squared over x squared. It doesn't matter. The 6x plus 8 doesn't matter. 6x plus 9, those things don't matter. As x goes to infinity, high powers dominate. Okay, x squared over x squared is 1. And it looks like, because remember, this is f prime we're talking about, not the f graph, f prime. So that's the slopes of the f graph. So as we go way out here, the slopes are getting closer and closer to 1. Does that look reasonable? Out here, the slope looks like it's 1, and out here, the slope looks like it's 1, right? So there's a line going right through here that it's approaching that has a slope of 1. So that seems reasonable. And, well, I think I just answered D. Okay, I think I just answered D. What does your answer, part C, tell you about the graph of f? It tells you that the slopes of f are getting closer and closer to 1 as x goes to infinity. That's what answer, part C, tells you about it. Okay. All right, let's go to packet number 2 and see what we want to do on this one. Speak up. Forever hold your peace. 1? No, sample 2. Sample 2. The other packet, yeah. Yeah, quick, yeah. Yeah. 4. If f of x equals this, then the fourth derivative is, there's an interesting little symbol. What is 4 exclamation point?
Factorial.
Factorial, which is 4 times 3 times 2 times 1. Right? Okay, so we got to know that. Now, I look at those answers, and it makes me think, okay, there's some sort of pattern. I definitely don't want to FOIL this all out and do any of that, right? So the first derivative, I bring down a 4, 2 plus 3. I mean, you can go all the way through all the derivatives. That's fine. But that's going to be the first derivative times a 3. You're going to kick out a 3. And every time you're going to kick out a 3. Now, I could take that 4 and that 3 and put them together and make it 12. But then I look at my answers. I'm like, do I really want to do that? Because I don't see that kind of number in there. Okay, so I'm probably just going to leave it like this. Now, remember, when you have a number out in front, it just hangs out there. So if you have 2 numbers out in front, they just both hang out there, right? So the 4 and the 3 are just going to hang out there. So now I'm going to bring the 3 down. So I got 4 times 3, and then I got my 2 plus 3x to the second. This 3 is just hanging out there. And I'm going to kick out another 3. Right, so you can already start to see what's going to happen. I did 1 derivative, and I got 1 3 hanging out there. I do 2 derivatives, I got 2 3s hanging out there. So when I do 4 derivatives, I'm going to have 4 3s hanging out there, right? First derivative, second derivative. So the fourth derivative, I'm going to have 4 3s hanging out there, right? And the first derivative, I got a 4. Second derivative, I got a 4 and a 3. The next one, I'm going to bring down the 2. And then the last derivative, I'm going to bring down the 1. I'm going to have a 4 and a 3 and a 2 and a 1. That's the 4 factorial. Right? Now, what happens to the 2 plus 3x? Well, when I do the next derivative, I'm going to bring that 2 down. I'll have a 1 there. When I do the last derivative and bring the 1 down, I'll have a 0 there. And 2 plus 3x to the 0 power is just 1. It's just gone. So I have 4, 3, 2, 1 here, and I'll have 3, 3, 3, 3, because I'll kick out of 3 every time, so it's going to be C. Okay? So that, I mean, you can go ahead and keep writing it down, but, so that's just kind of about doing a pattern and understanding what happens with your derivatives and those kind of things. Okay? Next. Yes. 7, really good problem. Okay? Now, we talked about this before, but it's been quite a while. Anytime, because what you're tempted to do when you read this, oh, it's a limit problem, right? And then you start thinking of factoring maybe, or can't, factor something out. You try to plug in an h right away. H plus h is, or excuse me, h approaches 0, so you put 0 in, you get absolute value of x minus absolute value of x is 0 over 0. Okay, keep going. Find something to do. It's a no calculator problem, so I can't graph it or do a table or anything. And you can, then what do you do? I mean, you check both sides. You can plug in a 0.1. Well, that doesn't really help any. I mean, that's, okay. So, this isn't a limit problem. I mean, it is. But you're not going to work it as a limit problem. Anytime you see a limit that has this look to it, what is that? What is that? It's a definition of the derivative. Only the single most important formula we've learned all year long. Right? It's the definition of the derivative. This is the slope between 2 points. The top is the two y values. What are the 2 points? X and x plus h, right? It's the y value subtracted and then the x value subtracted. Rise over run. The run would be h. Derivative, that's derivative. Remember when we used to do those problems? So if I gave you, now this one's a kind of a tricky one, but I've given you this before. If I've said, okay, what's the cosine of pi fourths plus h minus cosine of pi fourths? We did a whole worksheet on these. All over h. And then I ask you, what function is this the derivative of? And at what value are we doing the derivative? What was the a value? Remember that? Well, the a value is clearly the pi fourths, right? We're doing the derivative at that point. And what's the function we're doing the derivative of? Cosine of x, right? Cosine of x. So if this problem would have been this instead, whoops. If this problem would have been that, what you would look at is you said, oh, that's just the derivative of cosine, which is, it's derivative of cosine, negative sine, and then it's that derivative at pi fourths, right? Well, what's the sine of pi fourths? Root 2 over 2, negative root 2 over 2. So the answer to this limit problem would be negative root 2 over 2. That's how you do it. So in this particular problem, what's the function? Absolute value of x at 3. Now, the problem there is we don't have a formula for absolute value of x. Derivative. Well, you don't need one, right? All you need to do is think of the graph, right? What's the derivative of the absolute value graph at 3? 1. It's a slope, right? It's a slope. Slope of the absolute value graph at 3 is 1. So the answer to this is 1. A problem like this, we talked yesterday about how 65% gets you an A, so there's going to be some hard ones you're going to miss. You want to get the easy ones? This is supposed to be an easy one. I mean, after we've seen it a few times in a few packets, like the last packet didn't have one, this packet did, I'm guessing at least one other packet's going to have it. We're probably going to see it a few more times. In fact, it's pretty common. Not many tests, AP tests or whatever, don't go by without this question being in there. I mean, my God, it's a definition of derivative. It's, like I said, it's the single most important thing we've done all year, so it's not surprising they put that in. So when you see that, yeah, there are limit problems that you're going to have to do where you factor, try to do something, L'Hopital's rule, something like that. This ain't one of them, right? When you see that x plus h, that something plus h, right? As soon as you see that in a problem, man, you think derivative right away, okay? You think derivative right away. So this is supposed to be one you're saying, oh, this is just absolute value of x, derivative of 3, boom, boom, 1, move on. 10-second problem, you're on to the next one, right? I mean, that'd be the ideal scenario. And not have to miss this one when it's pretty given. Okay? All right. Next. Shout it out. That is next. I didn't mean literally next. I meant, the next one you have a question. Or is that the way it is when you have a question on every single one?
Yep.
Okay, well, here's one of those ones I talked about with they throw a B or a K or something in there and it kind of throws us off. Just pretend that's just any old number. Do everything the same as you would as if that was a 7 there or whatever. So this function has a horizontal tangent. Well, what's that mean? The slope, the derivative is 0. It has a point of inflection. It means a second derivative is 0. So that'd be a pretty good place to start right there. So y prime would be 4x cubed plus 2bx plus 8. And we're going to want to know where that's going to be 0. Well, that's going to be hard with that b in there. Well, so let's keep going. So they gave me more information. Y double prime, that's 12x squared plus 2b equals 0. Okay? That might be a little nicer. And it says they have that at the same value of x. So now we've got this thing equals 0 and this thing equals 0, right? So they have to be equal to each other, or we could just solve one. I mean, basically what we have here is two equations, two unknowns, right? Can we solve one and substitute for the other? Right? Doesn't that make sense? I mean, that's what we have here. We have two equations, this equals 0 and this equals 0, with two unknowns, x and b. Let's solve one for one of the variables and substitute in the other. I mean, that's just really, that's all it is. And so this one's a little simpler, so let's do that. So 12x squared would equal negative 2b, and it might be solved for b, so I don't have any square roots and stuff like that. So b would equal negative 6x squared, right? So now I should be able to plug that back into the other one. So I got 4x cubed plus 2. Now in place of the b, I'm going to put negative 6x squared, and then another x, and then a plus 8 equals 0. So I got 4x cubed minus 12x cubed plus 8 equals 0. Is that correct? I think that's correct, isn't it? So, oh, that's nice. I got negative 8x cubed plus 8 equals 0. So I'm going to subtract 8. Negative 8x cubed equals negative 8. So x cubed equals 1. So x equals 1. See? Is that the right answer? I don't think I gave you the answer. Yeah, they didn't want x, right? They wanted b. They wanted b. Okay? X is 1, but we can go right back to here. Put a 1 in for x. So b is negative 6. You're like, well, wait. That one I did on purpose. Okay? So not bad. I mean, it just, the calculus part of it was that. But again, that's think about it now. That's typically going to happen if you've got some unknown in a problem. They throw in a b or a k or something like that, and you're supposed to solve for it or find it. That typically means you're going to need two equations. It's going to be like a two equations, two unknowns kind of thing. You're going to have to find some way to get a couple of different equations with the information they give you where you can substitute. I mean, that's typically the strategy when you have an extra unknown in there. Right? That's what you do. And think about it. That's what Shanghai is about too, right? You've got these two unknowns, the x and the y value of what's going on that you're trying to find. And so you find your two equations, your two ways to do slope to be able to do that. I mean, so it's just generally that's the strategy. Okay, next, let me guess, 9. No? 9's okay? Okay, good.
10 and 11.
10 and 11. Okay? Let's we'll do 10, 11, then we'll stop there for now. So let f of x equal this at how many points in this interval, negative a to a, so that's, here and here, whatever, where that doesn't really matter, but I mean, that's kind of what we're talking about. does the instantaneous rate of change equal the average rate of change? Okay, two very important terms. Back at the beginning when we first talked about derivative, we put up two columns. We said here's algebra 1, here's calculus. You know, what's the difference between them? Well, algebra 1, you do average rate of change. In calculus, we do instantaneous rate of change. So instantaneous rate of change is what? At one point, not really close points, at one point. The derivative, right? Instantaneous rate of change is the derivative, the slope at one point. So, we need the derivative of that. So f prime of x is e to the x squared times 2x, right? Derivative inside. So that's f prime. And we want to know when that is equal to the average rate of change. What's average rate of change mean? Slope between 2 points. Well, what are my 2 points in this problem? Negative a and a, right? So what I need is a slope between 2 points. So I got to subtract my y's. How do I get my y's? I mean, the x's are easy. There's my 2 points, a and negative a. So I'm going to subtract, right? I got to plug them into here, right? Got to plug them into here. So let's plug an a in. Let's do the right one first. So that'd be e to the a squared minus, and then let's plug a negative a in. Negative a and you square it, what's that? Oh, that's just a squared, right? So that, oh, that's nice. So what's that equal? 0 over 2a, which is 0. Oh, okay. So there you go. I mean, this is going to be easy. So when does the instantaneous rate change equal the average? Because I thought it was going to get kind of messy there. But how does the instantaneous rate change equal the average rate change? Well, here's the instantaneous rate change, and we just found the average rate change is 0. So therefore, when does this equal that? So when does e to the x squared equal, or times 2x equal 0? Or how many times is what it said. Well, when does 2x equal 0? When x is 0. And when does this equal 0? Never. So, one time. One time. This never equals 0, right? There's nothing you could plug into there to get 0. E raised to the 0 is 1. E to the negative is 1 over something. Well, it'll never be negative. It's x squared. Okay. That's why the average rate of change was 0, by the way, is if you plug in, since you're squaring this, it's going to look like, the graph's going to look like it's going to go up over here, and then it's actually going to go up over here. So the slope between those 2 points is going to be horizontal. That's why that slope's going to be 0. Okay? But, I mean, so it's not really a surprise that it came out, the slope between the 2 points came out to be 0. So how many places in between is that going to happen? One time is the instantaneous rate change. Right there, down there at the bottom, the slope at a point is going to be the same as the slope between those 2 points. So that's why there's only one. Okay? But you didn't need to know a graph. This was a no calculator one, so you just work it out. Okay? All right, 11. Oh, yeah, forget about this one. Monday, we will be learning about the mean value theorem. Okay? So that's probably the only one we had that you really couldn't answer yet. Because that's one of those theorems. Remember I told you the last thing we do in chapter 4, we're going to do some of these theorems. We're going to do a couple tomorrow, and then we're going to do one on Monday, and then that's kind of wrapping up. That's about all the new stuff we have to do. Okay? All right, let's revisit the Newton's method stuff from yesterday, and let's pull that out. And I think you had to go, if I'm not mistaken, I think you had to go one more time, 3 more times.
Wait, where did you?
I had 4.
4?
I had to do it.
Yeah.
I did it a lot more times than you.
I can't remember the numbers, but the next one, let's see if we get some agreement. The next one was 1 point what? 225 something, and the next one was negative 1.2 1, well, it was like 3, 5, something, something. And then the next one was negative 1.2134. I don't remember, but I know after 3 attempts, and again, if you always rounded just the 3, then that was going to throw you off probably a little bit in trying to get the third one. So that's why you might have to go an extra time, right? If you wrote more than 3 decimals, you'll see. So that's when you know you're done. If you want to just go to 3 decimal places, you know you're done. Because from now on, it's only going to change out there in those farther out decimal places. Okay? All right. So, you're going to get a chance. You're going to get a chance to do another one where you make this table today and you can work together and help each other out. Okay? But remember what was going on here. Okay? Let me get this started so you can log in. Okay, so what was going on with this is we were writing that tangent line. Oh, shoot. I thought I started. Okay, so we make a guess. We ride that tangent line down to the x-axis. So when we're doing that last column, what we're doing is we're finding the place where that tangent line crosses the x-axis. We're hoping it's close to this actual root. And if we keep doing it and riding that tangent line, and that's where the formula came from, members, we took the line equation, we set it equal to 0, okay? And so if we keep doing that, then eventually the place where it's crossing the x-axis starts getting to be the same number over and over again because we're getting in really, really close to that point. Okay? And so what's happening on this thing, okay, what's happening here then with these numbers is we're getting closer and closer and closer to where this curve is actually crossing the x-axis. So we're finding the root of this particular function. And to 3 decimal places, it would be negative 1.213. Okay, now, if we can show that real quickly here. Did it let you log in?
Yeah.
Okay, perfect. And, okay, so let's go on the screen and solve. Let's go on your, everybody get your calculators out, and I'm going to show you a couple of calculator things that we can do. So let's solve that x cubed plus x plus 3. Yeah, go ahead, just type it in. X cubed plus x plus 3 equals 0. Go ahead and solve that. And there it is, negative 1.213411166, right? And so we found it. We found it by this Newton's method. But again, this formula, to remember, this formula came from taking the line equation, which is the slope at that point, and then just that point, and setting it equal to 0, and that's where this formula came from. Okay? So that's why when we do this little formula here, which we did in our table, that's why it's giving us the place where the line is 0, the place where the line crosses the x-axis, right? Which is finding that, then finding that, then finding that, and then just getting in closer and closer and closer. Okay, we talked yesterday about some problems that can come up. We talked a little bit about where you can cycle back and forth. You pick a number, the tangent line takes you over to here, then the tangent line takes you back to here, and you just cycle around. Or we talked about if you pick a number up here, the tangent line's not even going to shoot you there down to the x-axis at all. Of course, the formula, you can tell that that's not going to work because the slope would be 0, and you'd be dividing by 0 right there, right? If you pick a horizontal part. And then the other problem is if you just pick a point close to a peak. If you pick a point close to a peak, it's going to shoot you way, way out here maybe, right? And we'll look at a situation like that. when we got our super duper shortcut here. Okay, what is that? Okay. Probably should, but I know you guys want to keep working here. All right. Now, let's show a little bit of a shortcut here, and then I'll show you a really super duper shortcut. So here's how we could kind of shortcut this. So we had typed in, I don't know if you had typed f of x. Is that still in your calculator? So just type f of x for me and hit enter. Okay. Oh, it's not. So let's define it. So maybe you cleared that out. So the first step when you do a Newton's method problem on your calculator is you got to define your function. So let's define the f to be the x cubed plus x plus 3. And you can always check it by just typing f of x, hit enter, and it'll tell you if you've defined. Now type f of x and hit enter. Notice it's boldface. You hit enter and then it gives you that. Okay, and then g is the derivative. We want to name the derivative. So let's define g of x to be 3x squared plus 1.
What was it?
3x squared, just the derivative of that. So. Okay, so our formula is our x value minus the f value divided by the f prime value, right? Or we call it g. Now, so we always have to start with an initial guess. So this is called, so let's say our initial guess is going to be 1. It was this last time. So let's plug in a 1. Okay, so just type 1. No.
Oh, no.
We're going to follow this formula right now.
Oh.
So we're going to type in, so this would be shorter than what we did without writing out the whole table. Okay, I still want you to do the table at least, I think, one more time in your homework. So we do 1 minus, then fraction, and then we do f of 1, and then down there would be g of 1, right? And hit control enter so we get a decimal. And remember, negative 0.25 was the first thing we had in our table? And now we're just going to repeat that. So we'll go up and grab the negative 0.25 minus fraction f of, and then we can go up and grab that, or you can just type it, but it'll definitely get quicker here. Oh, whoops. Yeah, go up and grab it, and it'll stick it in there. And then down there, G, go up and grab it. Oops. I thought your cursor was down there.
So now it will. Okay.
Oh, yeah, that's too bad. Okay, so we got that. That was our next number, negative 2.5525. Okay, maybe we can if we just did divide. Huh? So negative, now you go up and now grab that, and then minus, and then let's just do, that's fine. And then here we'll go G, then we'll just have to type it for a little bit. Let's type about 6 decimal places. Or type. Okay? And now we got that. Was that the number we had? Is that something we had in our table?
Yeah.
Okay? Now, but on and on and on, right? And so we keep going. So again, you know, the people of Newton's day would be amazed that we could do this stuff, right? I mean, think about all those calculations. Even when we were doing the table, we were typing those in, and we were writing them down, and we were dividing. And then if you had to do that dividing by hand and all that stuff, what a nightmare that would be. But if your life depended on it, you know, or to get paid, or whatever your job, or you're a scientist, you know, whatever, you were trying to figure these things out, you know, this is what you did. But any ideas of how we can shorten this even more? Like that issue we had trying to arrow up to get our last answer here and get it pasted in here.
Could you define another function for f over 2?
Yeah. Well, that's a great point. That would save us there. Let's do that. So go to the menu and define h. That's a great idea. To equal f of x divided by g of x. Right? And so now we would just type in our well, let's go up and grab one that we already had that was pretty good. Let's go up and grab one up here. Grab that one. Grab that. Hit enter. Minus. And then it would, oh, that's fine. Actually, that's good that you did that. Grab that. And then hit minus h of that number. Right? Wouldn't that be doing it? Then we don't have to put it in there twice. Hit enter. Now grab that. Minus h of that number. Great idea. Look at that. Well, wait a minute. If we could define a function to be f over g, take it one step further. How about define it to be the whole thing? So let's do that. So let's define j
Oh my God.
of x to equal x minus f of x divided by g of x. Which actually we could put h of x because we already defined it. But let's just, this will look better. So isn't that, so our j of x is actually our Newton's method, isn't it? So now let's go back to the beginning. So we did j of 1. Okay. So let's say we want to plug a 1 into that. Okay. Now let's grab that. Let's go j of and then grab that. Probably hit control enter this time so we can get a decimal. And then j of. See, we're good at being lazy, right? We can find these shortcuts, right? The thing I told the other class, the old necessity is the mother of invention, right? That's how these things come up with, because somebody needs to be able to do a certain thing, and they say there's got to be a better way. And that's like Newton's method. Instead of trying to find the roots of this and guess and check and that kind of stuff, came up with this tangent line technique. Now, was it a nightmare to divide out and add all those different decimals? Sure. But it got the job done. I mean, eventually, after a lot of hard work, but it got it done, and it was better than just guess and check and not ever really know it. Now, with our technology, we've done this. Actually, there's a way we can do it even better. Look at the negative key on your calculator. What do you see there? ANS stands for what? More than just answer. The previous answer. Wasn't the biggest pain in doing this right now, going up and grabbing the previous answer? So, watch this. This is really cool. So we type in a 1, or do that. Actually, this is called seeding the calculator, because what we need is we need to get something into the previous answer, right? So hit a 1 and hit enter. So now 1 is our previous answer. Now where do we want to plug that? We want to plug that into, well, forget we did j. You're right, we could have done j. I didn't think about doing that. That would really be fast right now because we plugged into j, but let's pretend we hadn't went through that. Right here, we want to plug answer into these 3 spots, right? So here we go. So go second and negative sign minus f of answer divided by g of answer. Now hold it before you hit enter. Now we're going to hit control enter here so we can get a decimal. But now hang on to watch what happens here. So you go ahead and hit control enter. All right, now when you hit every time when you do a calculation, right, and hit enter, you can always then hit enter again, right? Now what's it do? You remember what it does? It does it again. It does the thing you just did again. And since the thing we just did was telling it to grab the previous answer, so now hit enter. And now hit enter. And now hit enter. Wow. And now hit enter. That is the super. Wow. That is the super duper shortcut, right? So what do you got to do? You got to seed the calculator. Right? You got to give it a first guess. And now that we defined J to be that formula, so now we can even short it more, right? We could go 1, hit enter. Right? So now that's in the previous answer. Now we want to plug that into J, which we defined to be this. So J of answer, control enter, 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 and so forth. Okay? All right. So that's pretty cool.
Well,
Now, here's the nice thing. Here's what's really nice about it is it allows you to do like what if things, right? Because in the table, you know, because what's going to happen is they're going to give you some problems. They're going to say, well, what if you started initial guess of this? What if you start initial guess of this? Well, if you had to do a table every time, you know, try this initially. I mean, even that would take a while. I mean, minutes instead of hours and days like back in 300 years ago. But it would just take one. But now this allows us. Yeah, I should. Yeah. So, but this allows us to now go in and say, okay, what would we get if we tried this? What would we get if we tried this? Okay, and see what happens. And that's going to happen to you on some of your homework. They're going to say, what happens with this initial guess? What happens with this initial guess? So in that case, I want you to do the super duper shortcut. Okay, so if you've already done what we did here, you defined your J function to be this, you're in great shape. The only thing you'd have to do with a new problem is what? Define. You wouldn't have to define J. You'd have to define F and G, right? So when you go to a new problem, you'd have to redefine F to be your function, define G to be your derivative, but J is still defined to be F, you know, X minus F over G, so you can still do that. Okay? And then you have to put in your initial guess and just hit enter, because what that does is seeds the calculator. That puts it into that answer variable. And then you still may have to go, when you start a new problem, you still may have to go J of answer. You know, you may have to type J of answer to get it started, you know, like we just did. Okay? All right. So that's Newton's method. Now, basically on our next quiz, I'll talk to you more about this later, but what I want you to understand about Newton's method, you're not going to have to, I think, maybe on the take-home, I haven't decided, maybe be one like this or something where you would do something with Newton's method. I might ask you something about it. The no calculator quiz that we'll do in class next week, I may just ask you about the process of Newton's method. So we'll review that more as we get closer. Just be able to describe or answer some questions about how Newton's method is finding that root, right? What it's doing, the process of writing the tangent line down there and repeating it, and how that happens or how that makes that work. Okay, I just kind of want you to understand that. Now, and then the other thing is why do we study it? Well, it's a cool use of the derivative and the tangent line, number one. And, you know, that's how your calculator works. When Matilda at the very beginning did the solve, which we all love that feature, right? Just solve, type in the equation, just gives you the answer. That's how it's doing, right? That some programmer behind the scenes has programmed this kind of it. Now, it might be something a little more complex than this to find it a little faster, but there's this repetitive kind of algorithm going on. Those of you that know something about programming, it's just a loop, right? It's just running through this process over and over and over again, right? Because the calculator can do all the parts. It can plug into the function. It can plug in. It can calculate the derivative. It can plug in, right? And it can do everything that's in there. So that's just written into the programming of the calculator. Okay? So when you type a solve, there's this stuff going on behind the scenes. So somebody had to understand this. You know, some programmer had to understand the mathematics behind this to be able to program the calculator to do that for you guys. Okay? All right. So today, what we want to do with the time that's left is some more work time on your packet, and there's a few homework problems out of the book with Newton's method, so we can do that too. Let's take a look at those. Let's open up to page, I think it's on 261.
Check one out, or just
You can log in. Okay, so here are the Newton's method. Here are the problems I want you to do. This is in section 4.6. Okay, there's 3 of them. Okay, so the first one is number 3. Number 3 just gives you a graph, and then it just asks you, okay, if you did Newton's method on this at these starting points, what would happen? So you just kind of look and kind of think, well, the tangent line would go to here, and then it'd go to here, and kind of see what you think, and just answer the question. So there's not anything to calculate or anything. Number 5 is one where you do a table. Okay, I told you we were going to do the table one more time. So it says use Newton's method, find a solution, and it gives you a function in the interval 0 to 1. So I would say use 0.5 as your first guess, right? Use 0.5 as your first guess and fill in the table like we did yesterday. I'll put it back up here on the screen. You will see. Okay? And then it just said, does this equation have any other solutions? Don't worry about that. So that's 5. So 3, 5. And then 15. 15 gives you a function, and then it says find each of the 3 roots. Okay? Now, I don't care if you use Newton's method or just solve them, whatever. I don't care about that. I mean, you do the super duper shortcut, you find it pretty fast. You just figure out you got to do different guesses. But to find, right, different guesses would lead you to different ones of those roots, right? Depending which guesses you start with, like I was showing you. You start with one near the peak and it takes you way over here. It may find a root that's way out there. Or if the first tangent line shoots down near this root, then it might find that root, right? So different initial guesses are going to find different roots. But then it says in part B, what happens if you use a first guess of 2? What happens if you do a first guess of 1.39, right? So that's where you do that super duper shortcut thing. And you try those initial guesses and just see what's happening on your calculator. Okay? And then just answer the questions from there. Okay, so 3, 5, and 15, and then work in sample 2. As much as you can out of the whole thing, really, for tomorrow is kind of what we want to do. Okay? So 3, 5, and 15 in section 4.6, sample 2, go to work. Just take that to the best.